Good morning, everyone. I extend my warm greetings to all the respected faculty, our esteemed speaker for the session, and all the enthusiastic participants on behalf of IEEE Student Branch. I am Sohan Kumar from IEEE D2 3x4, and it gives me an immense pleasure to be your host for today's session. Having said that, today's seminar would be an extremely insightful with the key takeaways, as our speaker would be addressing on the topic of advanced power converters for future power grids. It's more than a pleasure to have Dr. Rabiul Islam sir on board today, Faculty of Engineering and Information Sciences at the University of Wollongong University. His well-decorated achievements stand as a true testimony to his expertise, experience, and his contribution in this field. Without further ado, now I would like to request our HOD sir, Dr. Suresh Babu, to please take over and talk about our department and welcome the participants.
Very good morning to one and all. This is Dr. G. Suresh Babu, Professor and Head of Department of IEEE CBIT. I'm very happy to be amongst this galaxy of intellectuals, IEEE community today afternoon. That we welcome all the people, and 2 minutes about our department, which is a jewel of our college CBIT. The department IEEE started established in the year 1994 and progressed by leaps and bounds. Now it is having 2 sections, each of 60, and 1 PG program in power systems and power electronics. The main 4 pillars of the success for the IEEE department are: number 1, our dynamic principle and encouraging management, and non-teaching faculty. Out of 28 in teaching faculty, 12 members are with PhD and highly qualified non-teaching staff. And the second pillar is our students, very enthusiastic and interested towards, passionate towards subject students we are getting, sir, both current as well as alumni. That is second pillar of success of our IEEE department. And infrastructural facilities which we have in our campus, in our department, all labs we have. That is second pillar. Third one is our employers. People will come rush and make queue to take our students. All multinational companies, already 92% of placements is over in final year. So that is another pillar of our department growth set. Fourth, last but not least, we have interaction with industries, many industries. We have MOUs with around 8 industries, such as IMRC, HIEE, and CARES Renewables from Coimbatore, ISA Vyasa Technologies Private Limited, ISIE, Imperial Society of Innovative Engineers from New Delhi. We are proud enough to have MOU and work in the industry institute. Interaction is building up slowly with those MOUs. In addition to that one, a research component also added 1 more jewel to our department, sir. We have a research promotion scheme from AICTE to the tune of 12 lakhs and Modular project to the tune of 17 lakhs. Altogether, our students also involved in many research projects with idea labs and all. So this is what the scenario going on in our campus about our IEEE department in brief for the information of the others who are not aware. And this is what I welcome all the participants to this online webinar, listening to Professor Rabiullah from Australia, who is going to convert the power from one form to other form, power converters. So we're also power converters, sir. We are taking low power and we are converting high power to the students. By the end of 4 years, they will be fully powered with the placement and higher studies attitude. So we're also one of the power converters. Thank you. Over to speaker. Thanks a lot.
Thank you so much, sir. That was extremely informative, and all of us are extremely, proud to be a part of such esteemed department of a college. Having said that, now I would request Professor P.V. Prasad, sir, to introduce about CBIT's IEEE Power Electronics Society and the speaker as well. Over to you, sir.
Yeah. Good morning, all of you. This is Professor P.V. Prasad, the faculty advisor of IEEE Power and Energy Society. And we have started this IEEE PES chapter in our college in the year 2016-17. And since then, we are conducting many guest lectures, workshops, and then conferences also we have conducted. And continuously, the students are engaged in the various technical events conducted in our society. So now move on to the, we welcome you for the guest lecture, sir. So I'd like to introduce the speaker, today's speaker, Muhammad Rabiul Islam, received the PhD degree in electrical engineering from the University of Technology, Sydney, Australia. He is also senior member of IEEE, and he was appointed as lecturer with RUET Bangladesh in the year 2005, and later he was promoted to a full professor. In the early 2018, he joined at the School of Electrical, Computer and Telecommunication Engineering, University of Wollongong, Australia. He has published more than 200 research articles, out of which 50 plus are IEEE transactions and IEEE journals. And then he has written various technical books published by Springer, and he's also received several funding from government and industries, including the Australian Government ARC Discovery Project 2020, titled A Next Generation Smart Solid State Transformer for Power Grid Applications. He has served as a guest editor for the IEEE Transactions on Energy Conversion, IEEE Transactions on Applied Superconductivity, and IET Electric Power Applications. He has been serving as an editor for the IEEE Transactions on Energy Conversion and IEEE Power Engineering Letters, and also an associate editor for IEEE Access. So his research interests include power electronic converters, renewable energy technologies, power quality, electrical machines, electric vehicles, and smart grid. So thank you, sir, for accepting our invitation and presenting a guest lecture today for our students and faculty. Thank you, sir. Over to Sohan.
Yes, sir. Like I've mentioned, a speaker, sir's achievements are a true testimony to his expertise and experience. Like PV Prasad sir has mentioned all of them. I think those will definitely inspire us to contribute whatever little we can in this particular field. Before our speaker sir actually takes over the session, there are a few guidelines the participants would have to adhere to. The first one would be during the entire course of proceedings, please make sure that your mic is off during the entire course of proceedings, just because to avoid any kind of disturbance from your end, and the entire proceedings could be as smooth as possible. Your doubts would be definitely entertained. We will have a particular slot to take them, so please don't be worried regarding that. Having said that, speaker sir, over to you, sir.
Okay, yeah. Okay, welcome everyone to this lecture. And before starting to this lecture, I want to thank to the student branch over there, and also professors Prashad, Dr. Babu, and also head of the Department of Electrical and Electronic Engineering for their invitation and giving me the chance to present my work in this lecture. So as you know, this presentation basically covers the power converter technologies for future power grid. So in this lecture, I will try my best to introduce, that means first I'll mention what are the existing technologies, what are the existing systems in our power grid, and what are the challenges with those sort of things. And then I will try to mention or discuss how we can improve our future power grid, yeah, with the development of new devices or new systems. So what is the basic element in our power system network? We know the transformer is the very, very fundamental device, yeah, that we can see everywhere, yeah, in our power transmission and distribution network. If we consider a simple transformer, that means For example, the figure shown in here, this type of transformer we can see in our, the roadside or in our many places we can see in this type of transformers. So if we want to understand that concept, what is transformer and how it works, so this is just a simple information for you. So this is something, the construction, right? A simple transformer, it has simple primary winding, it has secondary winding, and then power transfer through the electromagnetic process. Yeah. So this is just something to recall our memories, right? So this type of concept very well established, and yeah, this device also very efficient. And if we look at our existing power network, then we can easily realize why we usually use this type of device, right? So in the power transmission and distribution network, in generation side, we use step-up transformer to step up the voltage from low voltage to medium or high voltage level. And in distribution side, we need also transformer for step down, right? The voltage, right? From medium or high voltage to low voltage. And also in many other places, we can see the application of this type of device in our homes or everywhere. For example, in power supply unit or in computer, we also need a smaller size transformer. So that's why I mentioned this is a really very common device or widely used component or device that we use everywhere in our power network. So what are the issues with this transformer? Especially if we talk about the environment, if we talk about the renewable sort of things, so then definitely there are some issues. So people already mentioned those sort of things. For example, these transformers are heavy and bulky, and these transformers require transformer oil, yeah, for the cooling purpose and also for isolation purpose, yeah. So if we look at in this table, so in this table we can see how big and how heavy these transformers are, and how much the liquid we need for isolation and also for cooling purpose, right? And definitely this liquid, transformer oil has environmental concern. So therefore, people are thinking how we can overcome those challenges. That means how we can design biodegradable type transformer, right? So that's the recent, actually, some sort of challenge based. If we think about the environmental point of view, then that's the major concern, especially when we want to use this type of transformer in offshore applications, right? So in offshore applications, if something happens or if there is a leakage of oil from the transformer, then that oil may pollute the environment, may kill several thousands of fishes or other animals in the offshore areas. So therefore, people are thinking to develop new type of transformer. Okay, on the other hand, if we look at the power qualities or the issues with our power networks, how good the quality of our grid power, right? So in many countries, especially in Asian countries, I know still the power not really very good in quality. I mean, grid power, not in very good quality. That means voltage sag, voltage soil, and definitely some sort of other issues, right, over there. Voltage unbalance, and also harmonics, oscillatory transients, impulsive transients, and nosing. So those problems are very common in our existing power networks, right? So this disturbance type mainly caused due to some sort of switching or load changing, or I mean, from the distribution side or from the load side, there are some sources to create this type of disturbance, right? For example, power electronic loads. So you see, nowadays we are using, I mean, more and more power electronics loads. So those power electronics loads basically introduce harmonics or inject harmonics to the grid, right? Similarly, voltage sag, it is due to direct online starting of the motors. If heavy motor start without any starter or current protecting devices, then definitely there is a voltage sag within that network. And the voltage soil due to sudden load removal, right? So that means these sort of actually changes or issues may create the disturbance in the network. So day by day, these issues becoming very serious. Why? Because day by day, the number of industries are increasing rapidly, and also the use of power electronics devices, the use of the other sort of, if we compare the loads, whatever we are using now and whatever we used around 20 years back, then we can easily realize there is a massive change in our load side. So most of our existing loads basically affecting the grid power, quality of the grid power. So, and if we look at the scenarios, how this, disturbance may affect the other loads, loads connected to that grid, right? What will happen if the harmonics, more than the acceptable rate or stable value, then what will happen? Then definitely motor overheating and some sort of other problems we will face. And also if there is a voltage unbalance, then definitely motor overheating problem. Similarly, voltage soar may create capacitor failure, right? And impulsive transients, if there are impulsive transients in the power network, then it will affect the electronic loads. May damage the electronic load in that network. So therefore, it is really important to take these issues and try to introduce something that can eliminate this type of disturbances from the network. On the other hand, if we look at the existing system, and if we look at the existing devices, what we are using in our traditional power grid, then we can easily realize that most of them are not really capable to handle those disturbances. For example, as I mentioned, the transformer, right? The traditional transformer, which are widely used in power transmission and distribution network. So this transformer cannot handle those disturbances and may affect, this transformer may affect by that disturbance, right? So therefore, this is the time to think about whether we can introduce a new transformer then that can handle those disturbances and also can mitigate those disturbances, right? Rather than affecting by that disturbance. So therefore, you see, as the traditional components cannot handle those power quality issues, therefore we need some extra devices to be installed in the network. For example, we need DVR, we need StatCom, we need UPQC, and many other things, right? To eliminate those disturbances or to save the devices used in power network. So those extra components basically increase the size, volume of the overall network, as well as increase the installation cost or running cost of the power grid. On the other hand, many of the existing devices cannot handle the ongoing demand or cannot fulfill the ongoing demand. For example, now we can see grid could be DC grid or AC grid, right? So if we look at 20 or 50 years back, most of our grids are only AC grid, no DC grid. But due to the large penetration of renewables and due to the large penetration of electric vehicle or other electronic loads, then people are installing more and more DC grids. So in this case, so our existing devices, whether these existing devices are capable to handle the DC powers or not, of course, no. For example, the traditional transformer, it can handle only AC, voltage or current. It cannot be used in DC network. So that means we need different device or different something to handle, for the DC grid. So therefore, this is the time to think how we can modify our existing transformer, or is it possible to develop a single transformer which can be used either AC or DC grid? And also the power handling capacity, power flow control capability. I think most of our devices, whatever we are using in the existing power network, are failing to do that job. But now, due to the, high penetration of renewable, this is the time to introduce something that can, confirm that issue. Okay, so here you can see the performance of different PV inverter, grid connected PV inverters. So usually the grid connected or grid tied PV inverters feed AC power to the grid, right? But if you observe very precisely the quality of the grid, the feeding power or feeding current, then we can realize that in addition to the AC component, it also injects some DC current. So what will happen if thousands of this type of inverters are connecting or coming to the grid, right? One or two inverter is not a problem. When thousands of inverter feeding power to grid, then definitely that could be an issue, because the thousands of inverter, if we combine all the DC components, then it may create a significant amount that may affect the transformer and other existing devices on the power grid or within that network. Especially if we consider some hours during the daytime, during the sunshine hours, for example, around 11 to 2 p.m. or something like that, that time in our residential areas, most of us usually going out and our homes, all the inverters with full capacity of generation and feed power to the grid. And that time, the consumption of that area or network is much more lower than the generation by those inverters within that area. So if it is the case or scenario, then what will happen? If the local generation, PV generation, is much higher than the local demand, then there is a chance to flow a reverse power from the transformer, right? That means the power will flow in reverse direction through the transformer. That means this DC component tries to flow through the transformer, and we know DC component cannot flow through the transformer core. That actually create the heat, right? So that means there is overheating of transformer core and may damage the transformer very quickly. So therefore, you see, for large penetration of renewable or these sort of things, then definitely we need something different technique or different devices or components to handle those issues. Okay, so have a look here. This is this slide or this figure basically shows the futuristic something. That means in future, what we will see in the power network. So this picture basically based on ongoing changes in our societies, right? So based on ongoing changes, we can predict, we can assume our future grid could be something like this. So in this slide or in this picture, what we can see, you can see somewhere high voltage AC network or medium voltage AC network. In some places, you can see medium voltage DC network, and somewhere you can see DC grid, and some places you can see AC grid. And here and there are different types of renewable distributed generations, and also battery storage, large battery in storage connection, electric vehicle connection, and use of different type of electronic loads. So if we consider this type of network, then you see some portion AC network, some portion DC network, and also they are interconnected. So how to interconnect DC and AC network? And if this is the case, then what we can see in future? Okay, just here. Yeah. So in order to interconnect those power electronic device-based loads, for example, electric vehicles, and also in order to connect those distributed generation sources or batteries to the grid, right? Using the existing devices, for example, transformer. So in addition to that transformer, we need the additional other components or devices. For example, in order to connect the renewable sources to grid, then we need power electronic converter or inverter, then transformer, then grid connection. Similarly for batteries and electric vehicles as well. And of course, for transformer protection, we need some other components, right, in order to protect or save or in order to improve the grid power quality. So from this picture or slide, it is very clear that these, non-traditional generations and these power electronics loads, right, actually making our network much more bulky and creating problems to handle or to control the network. So then this is the time to think about how we can simplify the network such that we can easily control, monitor, and we can ensure the reliability and other things. So here, look at this thing, right? So in this picture, consider a single device that may interconnect a number of either sources or loads, yeah, without using intermittent any other devices, right? So compare this, if we go with the existing devices, whatever we already have, then our network could be something like that. On the other hand, if we can introduce something smarter, then what will happen? Our grid could be, we can simplify our network in this way. That means we can easily interconnect all of these things through these common devices. That means this device can be used either in AC grid, either in DC grid, either for load, either for source, right? And it has multi functionalities. So yeah, in order to give you a clear information, I would like to mention something like this. Consider a mobile phone, right? Just about 20 years, if we go 20 years back, that time, if we can now find very old mobile phone in our house or in some shops, and then if we compare the current or latest version mobile with the mobile phone that we used around 20 or 30 years back, then what sort of things that we can easily realize? I mean, the function in terms of functionality or the size, volume, those sort of things. Then, of course, we can realize that if we have a mobile phone in our pocket, then we don't need many more devices. For example, we don't want any camera to carry if we go out. We don't need any television. We don't need any hard copy of paper. We don't need, computer to send messages or to check email, right? So mobile phone, now the smart mobile phone can handle many, many things. So this could be an idea, yeah, to compare or to introduce something for our power grid that will have the many more functionalities. Okay, on the other hand, if we look at the wind farm, especially offshore wind farm, because the onshore wind farm requires large areas of land. That's not possible, especially in these days. Therefore, large wind farm usually installed in offshore areas. But what are the problems? What are the challenges? Right. So challenges could be, you see, the netly, that means this wind turbine netly usually installed 80 meters above the ground water level, right? And this netly actually holds or mounts the transformer or other power components, right? So this is the simplified functional block diagram of a wind turbine. This is usually wind turbine blade and generator, then power electronics converter, and then we need transformer to step out the voltage and to feed the power to grid. And this transformer, you see, this is really very heavy and bulky. So in order to install that heavy and bulky netly above 80 meters, it requires, heavy investment, right? On the other hand, if we use the traditional transformer, then the traditional transformer oil could be another issue. That means we know the transformer oil should be checked regularly. So how critical to monitor the transformer oil in offshore areas? Definitely we need helicopter to monitor the transformer oil of that traditional transformer inside this neckly. That is very, very costly. So therefore the operating or running cost could be a serious issue. So therefore we can, what we can do, yeah, in this case, you see, actually in the previous figure, you can see here this power converter right? Power electronics circuit. This generator basically generate the voltage with a voltage rating 690 volts, for example, or something in between 380 to 690 volts. And if we go with the traditional converter, then this is the voltage rating for that converter. And then this transformer step up the voltage to medium voltage level, 11 or 33 kilovolt to feed power to grid. So what we can do, if we want to reduce the size and volume of this neckly and also reduce the regular monitoring, cost of this transformer, then maybe we can eliminate this transformer from the system, because this transformer just for isolation and for voltage step up. So if this converter can handle this operation, then why we need this extra transformer here, right? So therefore, people are thinking to eliminate that heavy and bulky transformer from the system by increasing the voltage rating or by proposing new type of converter here, right? Then you see, no need any transformer here. This converter can generate 11 or 33 kilovolt, right? And then this power can be fed to the grid directly without any step-up transformer. Yeah, so then definitely the question is, what type of converter technology that we can use to model this type of converter, right? So here you can see this is the two-level traditional converter technology. Yeah, that means if we go with this type of converter technology, then definitely we need step-up transformer to step out the voltage from low voltage or medium voltage to high voltage, right? So we don't want step-up transformer. We want to eliminate the step-up transformer. So in this case, what's the technique? So, multi-level converter recently actually taken people attention, right? Due to a number of reasons, especially with this topology, we can design medium or high voltage converters. And also, it has some other inherent advantages. If we compare the output voltage waveform of these two converters, for example, the converter output voltage, you can see on the top figure, right? So if we compare the reference signal with the output voltage, the output voltage shown in blue color, compare with the reference signal represented by red color, then you see lower harmonics means if the generated voltage waveform are very, very similar or very close to the reference signal, then we can say its the harmonic content is much lower, right? So in this case, you see for the multi-level converter, we see the output voltage waveform, it is inherently, you see, very close to the reference signal. That's why multi-level converter output voltage has a lower harmonics compared to the two-level inverters. On the other hand, you see, with this converter topology, you see here, you see a number of voltage levels. Actually, each IGBT or switching device handle only one voltage level, not all, total voltage level across a switching device. So therefore, we can use the commercially available low voltage rated IGBTs to develop high voltage inverter or converter. But with the traditional technology, it is very difficult. Yeah, people are using this topology to develop high voltage DC converter, right? So what's the problem with that? That means they actually connect a number of IGBTs in series, right? So then they apply high voltage here. But in this case, there are some serious issues, right? Because all the IGBTs should not be the same characteristics, but operating principle, operating characteristics or internal resistance or internal parameters. So therefore, very difficult to mismatch, and definitely there are some issues there. But those problems not really is, considerable for multi-level converter applications. So here you can see the that means price comparison. Yeah. So here you can see in this right side, basically I want to show you the price of the power electronic devices, right, based on their voltage rating. So here you see the voltage rating up to 2.5 kilovolt. You see the curve nature is something like this. That means it is not very sharp rise rate, right? But after or beyond 2.5 kilovolt, the power electronic switching devices, their price rating increasing sharply, right? So therefore, it is recommended to use the ICPTs lower than 2.5 kilovolt in order to save the overall cost of the converter, right? And also, the high voltage rated devices are not really mature compared with the low voltage rated devices. Yeah, and also here in the left side, I want to show you if we increase the voltage level of the multi-level converter, then we see the THD, total harmonic distortion, reduced significantly. So that means here, if we design a 11 kilovolt converter, and if we choose 21 level converter, then from this figure, you see the total harmonic distortion is less than 5%. That is the IEEE standard, right? So if the THD is less than 5%, that means without using any filter or line filter, we can feed power to the grid, right? So that's the another advantage to use this type of converter. That means no need any line filter to feed renewable power or distributed power to grid. Okay. Okay, so here you can see some very fundamental multi-level converter topologies. That means neutral point claim. Yeah, the left side figure shown shows the neutral point claim multi-level converter, and the right side one, that is the flying capacitor. This multi-level converter has some problems, right? So left side, you see this converter uses a number of diodes, right? So, diode reverse recovery could be an issue for this type of converter, right? So that actually affects the operation of the overall converter. On the other hand, the right side one, the flying capacitor, now the capacitor is bulky, and also its lifetime is much lower compared to the other components in the converter. So therefore, people are not really interested to use minimum capacitor in the system. So therefore, due to this high number of capacitor used in this topology, so people are not really focusing to use this type of converter in high voltage applications. On the other hand, cascaded multi-level. Cascaded, that means just only a numbers of haze bridges can be interconnected to generate the medium voltage or high voltage, right? So you see, just cascading of in numbers of haze bridge modules, right? That just like a full bridge converter here, right? And totally modular in nature. If you look at the circuit diagram, then you see just modular in nature, and they are interconnected, right? Or cascaded. And each of these IGBT just handle this amount of DC voltage, right? So therefore, low voltage rated devices can be used for these applications. And here, there are no auxiliary devices, I mean auxiliary diodes or capacitors here. I mean no auxiliary capacitors that I mentioned here, this capacitor and these diodes. So therefore, no those problems here, right? So, and yeah, but just one thing that I want to mention, within with this topology, we need a number of isolated and balanced DC sources. You see, DC source here, DC source here, DC source here, DC source here. So that means we need a number of isolated and balanced DC sources. That may be a problem, right? So, okay, I will come up with some sort of solutions to overcome this problem, right? Okay, so here you can see the output voltage waveform for 11th level converter, right? And with the different type of topologies, for example, neutral point clamp, flying capacitor, and modular multi-level, that means cascaded one, right? So here you see the left side, three figures, I mean waveform shows the output voltage waveform, right, for 5-level converter, and the right side three figures or waveform shows the output voltage waveform with the 11th level converter. Then you see with the increase, I mean with the voltage level 11, you see the output voltage, right? Output voltage is almost matched with the reference signal. That means without any filter, without any line filter, the converter output, you see, it is almost sinusoidal. So that means, you see, here we can say 7.07% TSD, right? So that means we need very small line filter to make it less than 5% if we go with this 11 level inverter. Okay, then here, just you can easily realize if we increase the voltage level, then how it can help to reduce the THD, total harmonic distortion, from the generated power, right? Here you see 9 level, then 11 level, then 15 level, 19 level, then this one is for 21 levels modular multi-level cascaded converter. This is the output voltage waveform. Yeah, this is just output voltage from that multi-level converter without using any line filter. No filter. The multi-level converter can generate this type of voltage directly, right? So you see, then this voltage, this power can be fed to the grid directly without using any line filter. Yeah, that actually helps to reduce the size, weight of the overall network, right? So here you can see the frequency spectrum corresponding to these voltage waveforms, right? So with the 21 level, we see the total harmonic distortion, it is less than 5%. Then you see it is already less than 5%. That means no need any line filter to reduce the harmonics less than 5%. It is inherently less than 5%. Okay, as I mentioned to you before, this type of converter, I mean, the left side, the circuit, right side circuit, you see, this is cascaded modular multi-level converter. As I mentioned, this converter, um, I mean, without any diodes and auxiliary diodes and auxiliary capacitors. That's why this one is more suitable. But only problem is it requires multiple isolated and DC sources. So then how to use this type of topology for renewable energy applications or for grid integration of renewable sources? Then you see, maybe as I mentioned to you, in order to interconnect a system to the grid, there are two things that we can consider. That is, one is the voltage level, and another is isolation, right? So if we want to interconnect our generating sources to the grid directly, right? So then we need to make sure those issues, that means voltage level, how to step up the voltage from this 690 volts to 11 or 33 kilovolts level, and how to ensure the isolation. So therefore, maybe we can use here high frequency magnetic link. It is a magnetic link, not a transformer. It is not stepping up or stepping down. Single 1:1 turns ratio, right? But single primary, multiple secondaries. So in this case, you see is secondary, then here in this module, you see the first block is rectifier and second block is inverter, right? That means we need this DC source. Yeah, just think about it. We need to this isolated DC source. How to create this in isolated DC sources? This is the option. This is the technique to generate multiple isolated DC sources. That means from single source to multiple source, then here AC, use this rectifier to convert it to DC, and then this hedge bridge means this hedge bridge actually. We can generate this DC by this rectifier and also from this secondary winding, okay? And the number of secondary windings depends on the number of DC sources required in this converter. Then we'll have medium voltage or high voltage AC from this side, and then we can feed to the grid directly, because we know the output power voltage quality is already enough to connect to the grid, because its harmonics less than 5%, therefore no need here the line filter. And also voltage level, it is already medium voltage level, then we can feed to the medium voltage level, and isolation through this high frequency magnetic link. And as it is high frequency magnetic link, therefore its volume and weight is much more compact. I mean, much more lower than the other system, right? Okay, so here another issue is how much power that we can handle with this type of topology. That means we use only single magnetic link here. then there is a question, how much power that we can handle? Can we handle 10 megawatt power with this single magnetic link? Of course, no. Maybe only 500 kilowatt power can be handled with this high frequency magnetic link, right? Based on the current technologies, we can think like this. So in this case, how to handle high power, right? So then maybe we can revise the previous circuit or topology in this way. Okay, so yeah. So here you see the total system here inverter this side, it is totally modular in nature, right? So that means this is module 1, module 2, module 3, and all are in parallel, right? So they are in parallel. Therefore, by increasing or decreasing the number of modules, we can increase or decrease the power handling capacity of this system. And here is module having this magnetic link. So this magnetic link actually for isolation and also for generating single source to multiple source. 1:1 times ratio. No step up, no voltage step up or step down here, right? And as I mentioned, this is high frequency magnetic link, which is much more smaller and lighter compared with the line frequency transformer. Okay, so and also this is a modular in nature. That's why if something happened to a specific module, then we can just immediately replace that module from the system and replace by a new one. And it is just nut bolt connection, just maybe 3 connection, 1, 2, 3, 1, 2, 3. Yeah, this that's why this is much more reliable and effective technology for this type of applications. Yeah, we already tested this type of technology in our laboratories, and we found very good performance, right, in our laboratory from our laboratory test. Yeah, and this type of technology can be used for solar PV applications as well. Yeah, so large PV farm can be interconnected to the medium voltage grid with this technology, right? So that means if we have a large PV power plant, then if we use this type of converter topology, that means you see the number of modules, it depends on and power handling capacity. Yeah, how much power we want to handle with this converter, right? So therefore, with this topology, there is no power handling capacity limitation or something, right? So and also, as the system is fully modular, then it is much more reliable than the modular system, right? And this topology also tested in the laboratories, and we found very good or interesting results to be push this technology for further. Yeah. So now come to the final point, that is as I mentioned in the beginning, that in future we will have different type of sources, different type of loads, and we will have DC grid, AC grid, medium voltage grid, low voltage grid, right? And also we will have electronic load, AC load, DC load, energy storage, those sort of things we will see in the future. Yeah, you can again have a look the right side figure that I mentioned. That is the prospected or that we are expecting in the future network, right? So in order to handle this type of network or control this sort of network, what we can introduce and what sort of technology that we can proposed. So left side, you can see this is a single, device. As I mentioned in the beginning of this lecture, right? How we can how we can think a single unit that can interface, that can handle, that can actually interconnect a number of sources, loads, or energy storage, and many more, right? So here you see, um, this is the high voltage side or medium voltage side, right? And here, this side is the low voltage side. That means low voltage DC is here, low voltage DC bus here, low voltage AC bus is here, and energy storage is here. So this is a typical scenario, but we can modify, we can change the circuit connections according to our requirement. Yeah. And here you see in the low voltage DC bus, we can interconnect PV, wind, DC load as well. In low voltage AC network, we can connect renewables and renewable sources, AC load there. Then we can consider this is the AC microgrid. Here we can consider DC microgrid. And here we can see the energy storage can be connected to this high frequency magnetic link. And power can be, power flow can be controlled and monitored through this magnetic link, right? So that means sometime when we have excess generation from this microgrid, then this power can be stored in this energy storage. And if we need some power here, then definitely from this storage we can pass from this storage to this AC bus or this AC microgrid through this network. So therefore, power can be flow in any direction, based on the system requirement or the system demand, right? And it is a fully, you see, electronic based. So therefore, it can ensure its, safety or its protection by itself. That means no extra devices is required to protect the system, and also has bidirectional power flow capability and can interconnect many more devices. Yeah. So this is something that we are going to develop, right, for the future. Great. Yeah. So if we look at what are the ongoing development of the industrial development in this sector. That means industries, they are actually helping by introducing latest power electronic devices. For example, silicon carbide. Silicon carbide, it can handle 15 kilovolt, and also it's a switching loss. It's switching on-off loss is much more lower than the traditional silicon-based devices. Its size is very compact. So therefore, it is not really difficult to develop that type of system in the future, right? So on the other hand, to develop the high frequency magnetic link, right, that's the another very important components or part for this type of technology. So good thing is that some industries, they already develop some excellent material. That means those materials are very, very high flux density, and also has a very low power losses, right? Core losses. So therefore, we can easily develop a very compact and high efficient magnetic link with that type of special materials. And usually this type of materials coming to our market, something as a ribbon, and that ribbon thickness is 20 micrometer. So we already tested this type of materials, and we found it is really a good and suitable candidate to develop high frequency magnetic link with this type of special materials, and its flux density more than 1.5 Tesla, right? So compared with the other materials, this materials is really high, has high flux density, right? And we also investigated, that means what's the type, shape that we can use to develop this type of high frequency magnetic link. So we considered different type of shapes, and then we investigated on that, and we found that toroidal shape could be a good option for us. And then now we collected some materials from those industries, and then we developed and tested in our laboratories. Yeah. And if we look at the B's curve, then we see how sharp, especially you see this B's curve for 10 kilohertz excitation. But if you look at the B's curve for other material, then that could then you easily realize that this material is much more, less core loss. That means efficient device can be developed with this type of material. Yeah. And then next question is, in order to use this type of magnetic link in the power converter, then definitely we need the parameters. That means inductance, and then other leakage inductance, and those sort of coupling things need to be properly calculated before using that magnetic link with the power converter. Yeah. And then another challenge is how many inputs or output that we can place, or we can connect with that magnetic link. That means what sort of topologies, that means dual active bridge, multiple active bridge, quad active bridge. That means how many input output ports that may give the better performance. That means better, more power density, right? Our target is to develop very compact, rigid, and high power density. Yeah, that's why we investigated those sort of things. Yeah, and we already investigated on that, and we found that the quad active bridge could be an option, because you see the penta-active bridge, that means 5 input-output ports on a single magnetic link. That's the difference between quad-active bridge and penta-active bridge. Not really, the change or increase of power capacity with the increase of number of ports are not really significant. That's why we suggest to use quad active bridge. Yeah, then we calculated the other parameters to set the control. Parameters, right? And we also tested those parameters and verified experimentally based on the step response excitation or those sort of things. Yeah. So I'm not going in details because it is already too much, I think. So I'm trying to finish within next couple of minutes. Okay, so then the next issue is the thermal related things, because the thermal issue is a really an important or critical issue for power electronic circuits. As our goal to develop fully power electronics based system, and this type of technology has hundreds or even more power electronic switches. So therefore, in order to improve the reliability, we need to confirm the thermal issues, right? So how we can model the whole system, the thermal behavior or sort of things. So therefore, we actually developed some thermal impedance modeling technique, right, on those type of converters, and then we tested and we found that those models can be used in these applications. Yeah, and also power loss division, that means equal power handling. That's another issue because we are using cascaded modular multi-level and you see now hundreds or even more power electronic switches. They are connected, sometimes cascaded and sometimes in parallel, right? So therefore, it is important to ensure whether all the switches are handling equal amount of power or not. Otherwise, some switches with more stress, some switches with less stress, then therefore you see some switches can be damaged earlier than the other switches that actually hampered the reliability of the system. That's why we need some modification in our control or switching technique to ensure the power loss division performance right. Then definitely control is an important issue in this yeah, special converter system, right? So as you see in this system, there are different sections. So different sections should have some local control. I mean, some sort of supervisory system should be there to ensure the overall system operation without any issues or problems. So here we actually investigated some control architecture, yeah. And we also investigated this concept for wind energy conversion system, and we created what is SOAL, SAG, and also harness those sort of grid problems intentionally, and then we check the performance, and we found that our system can handle those grid disturbances. That means, as I mentioned earlier of this lecture, what is SOAL, what is SAG, and other disturbances are very common. So we investigate that whether our system can handle, whether our system can minimize or eliminate those issues or not. And we found that our system can, effectively eliminate those grid disturbances, right? That means grid disturbance cannot propagate beyond that device. But with the traditional transformer, that or traditional devices, that disturbance can propagate even through the transformer. Yeah. Okay, we are now almost end of this lecture. Here you see as already you heard that we got a large funding from Australian government. Yeah, thanks government of Australia, especially Australian Research Council, to provide this funding to push this technology further. That means how we can use our converter, right, to replace the traditional transformer or even other component from the existing power grid that will help to make the system compact and improve the system control capability, which actually increase the reliability as well. Yeah, and also it is really important to have this type of technology in future. As I mentioned, almost all countries in the world are now pushing more and more renewable sources, right? And also electric vehicle and more and more penetration of renewable sources and electric vehicle actually putting our grid in some critical situations. So therefore, definitely we need this sort of technologies or technique to overcome those challenges. Okay, these are some photographs from our laboratories. We do research in electrical power engineering. Yeah, so especially power electronics, electrical machines, control for power system, right? Including electric vehicle charging station, and many more. And you are welcome to make collaboration if you have any interest in these areas, and also welcome to visit our laboratories and research center. Yeah. So that's it. Yeah, that's for today. Any question, any comments, please?
Um, Thank you so much, sir. Telling your content was very electrifying would be a mere understatement to say. Thank you so much for delving into the specifics of the topic and throwing light on the aspects which would in turn help us. Before moving any further, we would be taking questions, and participants who have questions, you can type your questions in the chat box.
Okay. Yeah. Yeah, I can see. Yeah. So I can see one.
I see a question here, sir. The question, I'll read it to you.
Just only one question there, right?
Yes, sir. Yes, sir. I'll read
Is
it for
it
you.
possible to use this type converter in large power plant? Yeah. So as I mentioned during my lecture, that our system is totally modular in concept, right? The topology, it is fully modular. So therefore, there is no power handling limitation, right? It can be designed for any power level, especially if we go back to this.
Hello.
Yeah, yeah, yeah. So here you see, if we increase the number of modules, yeah, module 1, module 2, module 3, module 4. So for example, each module can handle, for example, 500 kilowatt. So then based on that, we can calculate how many modules do we need to handle that amount of power, right? Yeah. Okay, so any more question? Okay, I can see more question there. Type your questions. Okay, please. Okay. I would like to, which type of converter can be widely used for marine application among different types like boost, buck, and other advanced topologies. So in marine, especially for offshore wind farm applications, so they, as I mentioned before, yeah, so how it is, yeah. So, yeah, yeah. So in wind turbine, we use the traditional two-level converter topology. Traditional two-level converter topology here to convert. You say this generator generating, I mean, variable frequency, variable magnitude, AC power, right? So we can't fit this variable frequency, variable magnitude, AC power to grid. So that's why we need first a rectifier to convert it to DC, and then we need inverter to invert the DC power to AC power, right? To fit to the grid. And now, after this converter, we will have constant frequency, constant magnitude, AC power, right? So this inverter, basically this rectifier and inverter, it is a low voltage rated traditional two-level converter topology, just like a haze bridge type of concept. That's why we can't go beyond this voltage level, or we can develop medium voltage level converter with this type of topology. So that's why now we are proposing a new type of converter here, such that we can generate medium voltage or even high voltage, right, through this converter without using a step-up transformer. Yeah. Okay, next one. Can we use this in microgrid for isolated connections? Yeah, of course. We can use this system for microgrid as well. Yeah. isolated connections. Yeah. So actually, we tested our system now in our laboratories as a just for solar applications. Yeah, solar PV applications, only solar, and then connected to the load. So this system can be designed or can be used for microgrid applications. Yeah, no problem. Okay, any other question?
So, seeing we do not have any further questions on Zoom and YouTube as well, can all the faculty and our HOD sir and our faculty coordinators turn on their camera so that we can take a picture? Okay, Karthik. Thank you for taking the picture. Now, I, on behalf of the entire IEEE student branch, would love to thank all the faculty and working professionals, and of course, the ever curious students for attending the session and helping it manifest the way we envisioned it to. Additionally, we extend our gratitude to our HOD sir, Dr. Suresh Babu, and our faculty coordinators, Dr. P.V. Prasad sir and Dr. T. Sudhakar Babu sir, for being pillars of support throughout the process. And more importantly, our speaker himself, Dr. Rabiul Islam sir, for making time for us despite being engaged and engrossed with a very busy schedule. It's been a day of learning, getting inspired, and going home with an extremely important takeaway. Having said all of that, now I would request our faculty coordinator, Dr. Sudhakar Babu sir, to take over and give the vote of thanks. Over to you, sir.
Thank you, Sohan. On behalf of IEEE CBIT, Department of Electrical and Electronics Engineering, Chaitanya Bharati Institute of Technology, Hyderabad, India, and entire fraternity of advanced power converters for future power grids here together, I feel immense pleasure to take this opportunity to give a propose out of thanks to our eminent speaker, Professor Muhammad Rabiul Islam, Faculty of Engineering and Information Sciences, University of Geelong, Australia, for spending his valuable time in sharing his expertise lecture and giving more ideas on various fields related to the converters, and which will surely help to the new researchers who wish to work their research carry out work in the related fields. I also wish to express my gratitude to the head of the department, G. Suresh Babu sir, and Professor P.V. Prasad sir, IEEE PS coordinator, for encouraging us to organize such wonderful session. I would like to take this opportunity to thank our student coordinators, Karthik and Sohan, for their wonderful support in organizing such event. Finally, I would like to thank our participants who have turned up in such a great number throughout the world and made a successful event on this evening. And finally, I would like to thank again one and all for being with us, and have a great day ahead. Thank you. Thank you so much, Rabiul Islam sir, for giving your expert lecture, and surely I hope it will be helpful to our researchers and students community who wish to work in this field of research.
Thank you very much, sir, Professor Rabiul Islam, sir. You have given a wonderful session on the advanced power converters. That too on solid state transformers, it is very coming up, and students have not studied in the regular curriculum. It was very helpful for our students for giving this wonderful lecture today. Thank you very much, sir.
Thanks for the comments. Yeah, that will actually inspire me.
Yeah.
Thank you, sir.
Okay, thank you.